So I used to live in London. I used to be a PhD student there.
Yeah.
And if you cycle through London, you'll probably know it's very dangerous.
Yeah.
I would always get hit by cars. People would walk out, and as a student, you don't have much money. And I always wished my bike would repair itself.
Okay.
And I thought, this is terrible. I keep damaging my bike. I keep having to pay to repair or replace things. What if it could fix itself?
Yeah.
And now what we work on is developing sustainable structures that can try to do that.
Okay.
So we incorporate organisms inside it. We try to understand how these organisms feel. And this tells us about the structural integrity or the state of the load of the structure.
Yeah.
But also we try to see if we can reinforce it locally.
This is Coffee with Martin, where aerospace conversations take off. In this episode, we explore a different kind of engineer, one that has been shaping structures, materials and systems long before we even started designing aircraft. Nature. From the strength of bone to efficiency of cellular structures. Nature has spent millions of years refining solutions to challenges we only just beginning to understand. But what happens if we try to translate those principles into aerospace? How do you move from inspiration to application, from complexity to manufacturability? And what does it really take to design materials that are not only strong and lightweight, but fundamentally smarter? Today I'm joined by Kunal Masania, full professor at the Department of Aerospace Structures and Materials, with a focus on bio-inspired materials, and Baris Caglar, assistant professor in the same department. Where Kunal focuses on learning from nature, Baris brings those principles into practical, manufacturable structures. Together we explore what it means to learn from nature and what it takes to bring those lessons into the air. Let's get into the conversation. So welcome Kunal, Baris. And my first question is always in this podcast, what kind of coffee do you drink?
You go first. I have a very long answer.
Yeah, the short answer is any and a lot.
Okay.
Longer answer, I like North African coffee,
Mm-hmm.
and I like Colombian coffee. So
Okay.
I prefer like a bit more intense, a bit bitter taste
Yeah.
behind. Yeah.
And do you drink like espresso or filter or?
Depends on the time of day.
Yeah.
So I start usually with a really good flat white.
Yeah.
Start at home. Then come to work. Then I will switch more to a, let's say, Delft filter coffee
Yeah.
style. But then, of course, break the day with a latte or a macchiato or something. Yeah.
Okay. Cool. And for you, Baris?
So I thought my answer was long. No, my answer is really longer. I'm Turkish and we drink lots of tea. For 10 years or so, I replaced tea with coffee. But since March 2025, I'm not drinking coffee. And there's a story behind.
Ah.
Like, I have a kid, you both have kids.
Yeah.
You know how it goes. On Saturdays, you go out and you cannot have coffee until noon.
Yeah.
And then you have a headache,
Yeah.
right? And I realized I'm starting to associate it with being with the family. No, I'm kidding. So that's one aspect. And the other is I got sick and I couldn't drink coffee in March 2025 for a few days. And I decided that I'll just survive the pain for a week.
Yeah.
And drop the coffee completely
Okay.
because I was an addict. Like I was having 5 a day.
Yeah. So after 1 week, the addiction is out of your body.
Exactly. Since then, I didn't drink any.
Okay.
So no coffee,
Right.
black tea,
Ah.
preferably Turkish. Otherwise,
With sugar, without.
without.
Yeah. Okay. Yeah. Okay. Cool. Thanks, guys. So my second question is, can you introduce yourself in one sentence? And you can think about it.
Yeah, sure. I can introduce myself. So I'm interested in how nature makes materials and structures.
Yep.
And I'm interested in capturing some of the features that organisms have into engineering problems, let's say.
Okay. Cool.
On my side, I'm interested in composites that are sustainable, aerospace materials, and how to make the manufacturing processes also sustainable, more energy efficient, etc.
Okay. So I think, Kunal, let's start with you. Can you give an example of your research, of your nature into engineering?
Yeah, sure. So we do a lot of 3D printing. And if you look back at the origin of 3D printing, the whole idea of it was to create self-replicating machines. And they were inspired by how organisms self-replicate.
Mm-hmm.
And now we have developed all kinds of printing processes, new technologies, different materials. But what lacks is that the processes are not resilient. So you send a file to the printer, you pray, and either you're going to get spaghetti or you're going to get an object. You know?
Yeah.
And one of the things we're now doing is realizing that when things grow, they are not just single instructions sent to the organism to make something, but the thing is dynamic. It will adapt. And we're trying to incorporate that into printing technologies now.
Okay.
So to say good enough is fine, as long as we know what it is, and allow the process to adapt according to what is being manufactured on the fly.
Okay. And what makes the structures from, let's say, nature so efficient that we want to replicate it?
It's the being frugal with the material that is used, so using minimal material, leveraging anisotropy. Organisms are really good at this. And it's about designing with resilience, so that you don't over-engineer the structure, but you rather let the structure adapt on the fly during its lifetime.
Yeah. And why is it so hard to reproduce that complexity?
The level of self-organization is at the nanoscale.
Yeah.
So if we want to build and engineer with this, then we need manufacturing technologies also capable at this kind of resolution of control. And all of these materials have sentience. They can think and feel, but typically our materials do not. So there's quite a fun gap to solve, which is how do we create, we call them smart materials or functional materials.
Yeah.
But it goes way beyond that.
Okay. And Baris, you look at composite materials.
Yeah.
Can you give an example of your field of research, or what kind of research do you do on the composite material itself?
Yeah, on specifically how we make things more sustainable.
Yeah.
So I can give two examples. One more on the material side, the other more on the process side. And on the material side, we, like many other people, we are looking at thermoplastics to replace thermosets. And what's unique in our research is we have the capability and we have the interest in looking at the unidirectional materials. That's kind of the building block of the thermoplastic composites, because that's where you define most of the properties, and these materials are also suitable for automated processes.
So you go back to the building block, Lego block of the composite.
Exactly.
Yeah.
And we know that the thermoplastics are inherently more recyclable, so that's why we specifically look at the thermoplastic.
Is that the main reason why we want to shift from thermoset to thermoplast?
That plus the suitability for automation. Because if you want to build 4 times more aircraft, you don't want to build 4 times more factories, right?
No.
I mean, of course, the companies would like to employ as many people as possible, but also they would like to deliver on time. So we definitely need automation for this.
Yeah.
And these materials are also suitable for automated processes.
Yeah.
So that's the material side. And on the processes side, but there's the reality of thermoset composites. They'll be with us for a while. We won't replace them with thermoplastics right away.
Mm-hmm.
And for thermoset composites, we look into very energy efficient processes, because the thermoset composite manufacturing process is like baking. You put the right materials together and then you put everything in an oven.
Yeah.
And if you want to bake for 4 people, you need a small oven, right?
Yeah.
But if you are baking for the whole family, large
Need a big
family,
oven,
then
yeah.
you need a bigger oven. Same applies to the composites, to aero structures.
Yeah.
And we look into processes where you can locally initiate the baking process, and the composite keeps baking itself
Mhm.
until it reaches the desired strength.
Yeah.
And these are, I never did the detailed math, but it's like 1 to 2 order of magnitude more energy efficient
Okay.
processes. And we specifically look at a process called, a curing process called frontal polymerization.
Okay.
Yeah.
Maybe you should explain that as well while we're talking about it.
Yeah, it's as I said, I called it self-baking. We call
Yeah.
it also an autocatalytic process. And typically you literally put everything in an oven and cure everything, and cure the thermoset material in the oven. In this process, you have the right chemicals in your system, so that when you initiate the curing process from a corner, let's say of a table like we are
Yeah.
leaning on at
Yeah.
the moment,
Yeah.
you initiate the cure process from a corner, and then the released heat from that corner initiates the curing process of its neighbors, and
Yeah.
this goes on and on and on
Yeah.
until the whole table is kind of cured.
Like a fire.
Like a fire,
Yeah.
yeah. It also self-propagates.
Yeah. Yeah. Exactly.
But we don't want that.
No. You want to control that
Yes.
heat, right? Yeah. And if you look at composite manufacturing, how different is that from the standard technologies for manufacturing in steel or manufacturing in aluminum?
That's a good question. The difference, I mean, the way I see it, the main difference is we know humanity knew about metals for a few thousands of years,
Yeah.
right? So the manufacturing processes are kind of mature, more mature than the manufacturing processes around the composites, because carbon fiber has been in our lives since roughly 60s.
Yeah.
So that gives us 60 to 70 years.
Yeah.
You can imagine how much there's potential to improve our manufacturing processes. So that's one angle. So we are learning,
Yeah.
definitely. The other angle is the metals are typically processed or manufactured. Parts out of metals are manufactured by subtractive processes. So you cast things and then you machine, typically.
Yeah.
And then you bring parts together.
Yeah.
And in composites, we start from fibers that are like 1/10 of the hair in diameter.
Yeah.
And then we try to make wings out of this. So we bring tens of thousands of these fibers side by side and make fabrics out of those, woven fabrics, etc., or unidirectional fabrics.
Yeah.
And then to keep them in place, because they are very strong, as they are 1/10 of the hair, but they are 8 to 10 times stronger than steel.
Okay.
So we want to keep them in the right shape. So
Mhm.
for that, we introduced the polymers, the
Yeah.
thermoset or
Yeah.
thermoplastics. And so bringing these two materials together while making sure that everything is at the right place,
Yeah.
but not elsewhere, and to make sure that we don't have defects like voids, etc.,
Yeah.
is complicated. And there are a few length scales at play.
Yeah.
As I said, the fibers are 1/10 of hair, so 7 to 10 micron. The spaces are even smaller. And then from these, we go to parts that are at meter length,
Yeah.
close to meter length, and then we produce components or structures that are
What is
tens
the
of
what is
meters.
what is the typical wing length of an aircraft?
It can go to 30 meters
Yeah.
easily.
Yeah. And are we there yet to make these full structures from this composite material?
In terms of like if we were to make a monostructure, a monocoque body, I think we have the knowledge
Yeah.
to bring the materials together, but then reality is a bit different, right? Because if you try to do that, the cost skyrockets. So what we do is we produce parts and then we bond them, we glue them, we rivet them, etc., etc.
Yeah.
And then for specifically talking about aerospace, for large aircraft, this makes sense because there is always the business perspective.
Yeah.
For the large aircraft, the additional lightweighting you get from these materials and the increase in cost, because it's a bit more labor intensive, it pays off. But for this, typically for the single aisle aircraft, for instance, we are not there yet.
Where does your research meet each other, or where is the gap, or where is the, I would say, the fight, but there's no fight between you, but where's the discussion between you? Where does your field of research meet?
Yeah, I think where we meet is it's really rather organic. So I'm really interested in making materials and manufacturing processes more bio-inspired and more resilient and more adaptable. And I think Baris's interest is how to make them more applicable sooner, and also how to leverage data that they are more reliable.
We have a joint PhD student that Kunal promotes.
Yeah.
Shanta, and her research is a good example. She's working on the industrial scale 3D printing or additive manufacturing with polymers. So in this case, we are talking about polymers that are deposited with a width of centimeter, roughly. And Kunal's research comes into play in developing the whole process.
Yeah.
And understanding and controlling the material behavior. And my research comes into play at looking at the process and making it even better using the data that comes out of the process.
And you say together with industry?
Yeah.
How does that industry is involved in such a research?
So this specific PhD position is funded through a national consortia called Next Gen High Tech.
Yeah.
And there we collaborate, we work closely with industrial partners.
Yeah.
And in this specific case, there is a industry partner that develops the 3D printing heads, who is interested in the outcome of our research.
Yeah.
And Semexcel hosts one of the 3D printing heads.
Yeah, the robotic field lab.
Yeah. Robotic field lab Semexcel, where they mounted the printed head on a robot, basically. And Kunal and I do the research part. So there is an equipment that from an industrial partner placed at a field lab, which is being used by two professors at Aerospace.
But is the question or the problem statement comes from industry, or is it research driven?
It's both. There are the needs of the industry because, that company is filled with smart people as well. So they solve lots of problems that they are encountering on a daily basis. But it's typically taking a trial and error approach, I would say. And we are coming into play to maybe take a step back, look at the data, look at the fundamentals of the process, and develop the methods so that the industry can use the generated data and generated knowledge when they are designing a new part, for instance.
If you have this crazy research idea, how does it come to you? Is it like when you're on the bike to home and think, hey, I'm going to research this tomorrow, or how does it come to mind?
Yeah, I think it's very individual. My PhD student, she told me it was always in her shower. She would get her best ideas.
Yeah.
For me, it's indeed on the bike home.
Yeah.
Where I have to sometimes stop and write it down so I don't
really?
forget. Yeah.
And can you give an example what you wrote down halfway the trip?
Well, it's actually what I'm working on now. One of the major things we're working on.
Yeah.
So I used to live in London. I used to be a PhD student there.
Yeah.
And if you cycle through London, you'll probably know it's very dangerous.
Yeah.
I would always get hit by cars. People would walk out, and as a student, you don't have much money. And I always wished my bike would repair itself.
Okay.
And I thought, this is terrible. I keep damaging my bike. I keep having to pay to repair or replace things. What if it could fix itself?
Yeah.
And now what we work on is developing sustainable structures that can try to do that.
Okay.
So we incorporate organisms inside it. We try to understand how these organisms feel. And this tells us about the structural integrity or the state of the load of the structure.
Yeah.
But also we try to see if we can reinforce it locally by promoting the organism to grow and add material where you need it.
And how far are you in this research from idea? Is there like an experiment, or is it a proven technique, or can we see it? Can we feel it? What is the stage of this typical idea?
We're about halfway through the project. And as is typical in science, like you read papers and you think, oh yeah, that we can do that in the lab. Then you try and you realize all the previous literature is wrong. So you
Okay.
have to start again.
Yeah.
Redo the fundamentals, and then hopefully you can apply it to a problem. So we're now at a stage. So we work with fungi, living materials.
Yeah.
We're at a stage where we can reliably interpret the signal. We can eliminate noise from the signal, so humidity changes, temperature changes,
Mm-hmm.
magnetic field changes. And now we have a platform that we can really do mechanical tests on and relate the signal from the action potential of the cells to a structural load case.
So self-healing materials. So on this coupon level, you make a scratch, or you make a dent, or you make a gap, a hole, and then it heals itself, or how?
Yeah. So what happens is so mycelium fungi,
Yep.
they have a signaling network. So they are interconnected cells in a mesh, and these cells, they pulse an action potential, and it propagates as a wave through the material.
Mm-hmm.
And there is a short duration, long duration. There are two frequencies.
Is it like a heartbeat?
It's more like a neuronal activity of your brain cells.
Okay.
Spike-like behavior, right?
Yeah,
Like
so
a signal.
Yeah, you really get an action potential.
Yeah.
So it shoots up.
In case of an
depolarizes.
event.
It all the time.
All the time.
All the time.
Yeah.
As long as it's living, all the time.
Yeah.
And that's how it kind of guides its morphogenesis. So it kind of decides where to grow more.
Ah.
And when you damage it, the signals all point to the damage and say, okay, first seal the cell. Okay, now add more enzymes to remodel the cell wall, and we will repair. And then they start growing. So you really promote growth when you create damage.
Yeah. And then fast forward to, because we're part of the aerospace faculty, when can we apply this on an aircraft, or what is the next step? Do we first do it on a car or on a bike, like you described in London, or
Yeah.
what is the timeline?
Yeah, if I go back to a comment that I made right at the beginning, aerospace is quite conservative. So to apply to an aerospace structure, I hope in the future we can, but yeah, I think we need to prove it and test it well first. Typically, you can apply these new technologies first into sports and leisure industry, where they are really innovating every year. They want the newest, coolest stuff.
Yeah.
And I'm imagining, if it would be successful, to first apply it as a health monitoring for the structure.
Okay.
So not to modify the structure, but just to understand stress distributions.
Yeah. Is it also maybe I'm thinking about space. We send a bunch of fungi into space and it builds structures by itself, or is it? Am I dreaming?
No, you're not. No. So there's a lot of research from NASA in California, also from the UK.
Mm-hmm.
They're really interested to build habitats. Also at Delft in
Yeah.
architecture.
Okay.
They're
Yeah.
really interested to build habitats. And then these fungi cells are really interesting because with very few cells, you can
Mhm.
create a huge biomass
Mm-hmm.
if you have the nutrients for it. And so the idea is to bind regolith or Martian dust together and use it as the start of
Yeah.
habitats. Yeah.
Yeah. Cool. Before you start an actual project, there's a whole bunch in between, right? So you convince your colleagues or convince PhD students
Yeah.
to work on it, or
Yeah, you tend to have, PhDs tend to have their topics already defined, right?
Yeah.
You always maneuver a bit
mm-hmm.
because, like, it's research. You start with an idea and it doesn't materialize, and you take a turn or you decide to take a step back because, as Kunal was saying, the literature is completely wrong and you have to start from scratch, kind of.
Mm-hmm.
But I tend to start with master thesis, typically.
Okay.
So that's the first small step.
Yeah. And then you make an
new ideas.
advertisement to the students saying, "Hey, I have this cool idea. Who wants to research this?"
Yeah, that's one of the things we do in the department. We literally pitch our
Yeah.
ideas to the students in these networking events.
Yeah.
And there we get some traction from
Yeah.
the students. And also I think it's the natural process that as I'm teaching more and more, the number of students that know me, that know who I am, that know how I operate, etc., is increasing.
Yeah.
And I also get students reaching out to me
Yeah.
to work on projects. Then I start by asking, numerical or experimental? And then if it's experimental, then I have a list. I also take notes, of course. Then I have a list. If it's numerical, then I have another list.
Yeah.
I mean, numerical nowadays is AI.
Yeah.
For AI for manufacturing processes. Then from there we work on, right? And that's typically the first step. And then at the same time, we always, I think, as Kunal was saying, we know each other well, but we also have quite some differences.
Yeah.
I'm also interested in processes that are closer to the industry. So I always have this eye to have a sanity check from the industry. Like, is this something that they would be interested in or not?
Yeah.
I do that as well, but that doesn't stop me from doing
more
or
experimental
investigating really crazy ideas with the master thesis.
Can you name a crazy idea?
Crazy idea. One thing that we also discussed with Kunal back in time, like there are these things called heat pipes that are used for dissipating heat in structures. It's used, it's a technology used a lot in cooling down CPUs, GPUs, and also in
computers.
space. Yeah. And I wanted to make a heat pipe out of a polymeric system or a composite eventually.
Yeah.
And in this case, it was me who did the experiment. Sorry, not a student. And it worked out. So I had a half-working prototype. Nowadays, it's idle. We don't have any students working on the topic, but I feel like we might revisit at some point.
Push it somewhere.
Yeah, exactly.
And it triggers me that you say we do like a sanity check with industry, right?
Yeah.
So because we're working at low, we do experimental research, right? When there's something becomes technical feasible to scale it up to industry, who decides that, or what is the process of that for you both? I think.
Yeah, there's a push and pull process, right? We have a PhD student, for instance, working on. Again, I will go back to the unidirectional tape topic.
Yeah.
So we have this research facility where we do the research on unidirectional tapes, and we have a PhD student who is working on sensors to monitor the tape manufacturing process, so that we can quantify how much or how much more or how much less fibers or polymer are there in a cross section in a given position on the tape.
Yeah.
Along its length, along its width. And so we've been developing this because we were interested ourselves. But then if you talk to the industry that produces the tapes, what they do is they register a similar information across the width every few meters.
Yeah.
So when they register this variability, they get a number out of it, so an average.
Yeah.
And then they do this every few meters, and they take the average for 1 kilometer length of tape.
Yeah.
Right? And then they take basically the average of an average.
Yeah.
And they give one number to the customer, like the OEMs who produce the
for the specification
aircraft,
of the
right?
material. Yeah.
But nowadays, where we are standing, everyone realizes that we need more, because we want to register the slightest variability in the material we are putting in the components, so that we can either modify our manufacturing processes, or we'll know which region, which section of a part is more sensitive than the other.
Yeah.
So we've been doing this bottom-up research, and now we are realizing there's interest from the industry because we are talking to them. They are telling us what they do.
Yeah.
We are telling them what we do.
At that point, industry only knew that one variable that comes with that specific material.
Yes.
But you went into 1 or 2 layers deeper. Maybe a question also for you both is how will an aircraft look like if you merge design, the material, production, completely into one integrated, let's say, shape. Can you elaborate on that? Maybe, Kunal? You understand my question?
I think so.
Yeah.
Yeah, I think every aircraft will look a bit different because the process is inherently variable and so is the material. So if you have the level of understanding that Baris is explaining, then whilst manufacturing, you can really modify the geometry or the structure according to what the material exactly is doing.
Yeah.
Maybe when they're parked at the airport, you will not see a difference, but there will be a difference programmed into the production.
Yeah.
For sure.
And if you look at an aircraft, what do you see? Do you see like all these challenges to upgrade the aircraft, or?
I see a lot of joints. I see a lot of black metal engineering.
Yeah.
A lot of holes where there should not be.
Yeah.
I think if we already solve this, we will save a lot of weight.
Yeah.
But with that, we need to add resilience to the structure.
Yeah.
So we need full field spatial sensing everywhere on the geometry so that we know how the aircraft is feeling.
And if you look at, let's say, the first generation aircraft, let's say 50s, 60s, right? So when people went to a business trip or holiday, flying a large amount, compared to today, do you see a big difference in the aircraft structure, or is it still the same?
I mean, I think visually they look similar, but it's with very good reason that they're designed this way. They're designed to be very safe.
Yeah.
So that if there is an emergency, then the people are protected. The engines are way far away as possible from the passengers as well. Fuel is stored in the wings usually, again, to keep away from the passengers.
Yeah. So safety is driven the design of an aircraft.
Absolutely.
Yeah. And what do you see, Baris? If you look at an aircraft, or the comparison between old and, let's say, the newest
the
generation.
old and the new, as Kunal well said, it has been tube and wing.
Yeah.
It is still tube and wing.
Yeah.
But I see lots of research on the blended wing structures,
Mm-hmm.
which have been demonstrated at the model scale.
Yeah.
I'm really looking forward to the future where I can fly in a blended wing aircraft as well.
Yeah.
And I think the knowledge is there, but of course, it's like the elephant in the room. We never use the word in the last 45 minutes or so, but certification or qualification of the right materials, the right monitoring techniques,
Yeah.
and manufacturing and monitoring everything will be the real challenge when we go from tube and wing to the blended wing concepts. And then, as Kunal said, the structure will have to be much smarter, and from the outside the aircraft will look identical, but on the inside there will be lots of differences.
Yeah. So technically it can be possible, but then on the certification bodies that regulates the safety of our aircraft should be convinced or should be proven, or should these people or these bodies have a different mindset?
I think they have the mindset or the certification processes for a good reason. If you look at the number of accidents, deaths per kilometer, etc., it looks like it's paying off. But to do a full circle to the beginning of the session, I think we can find, like as Kunal does a lot in his research, we find inspiration in nature, in topology optimization, for instance. But then the load pads in organic structures are also organic, right? You have like branches, trees that divide into smaller branches.
Yeah.
And these are either organic. The load is, it's flexible in one part, hard in the other, etc. And we know how to make structures and how to bring the right type of materials together to produce such structures.
Yeah.
But the challenge will be certifying those.
Yeah.
Because the certification process expects more predictable load pads which means usually more straight lines than organic curvatures.
Yeah, exactly. So more engineering than nature.
Yes.
Yeah. And maybe Kunal, I think, what is the first thing we're going to see on an aircraft that is inspired by this way or inspired by nature? That is going to be certified and safe. And
Yeah, I think aero elasticity and morphing is quite advanced already.
Yeah.
And I'm really excited that the next generation of aircraft will have more intelligent wings which can adapt a bit to load paths, to aerodynamic loads.
Yeah, like a bird.
Yeah.
So it's make your wing adjustment for the load path at that point in time. You can adapt.
Yeah.
And maybe a general question, because can you both describe a moment, let's say, in your career that was life changing? You already told the bike story in London, right? But more because I think you chose the academic track for a reason, right? You're not working at a company. What was a life changing moment in your career or during your research that was like, this is really cool. That's why I'm here.
Good question. Go on.
Maybe I can start. So I'm also like a pure composite materials engineer from background, and I got really frustrated that we can only make planar things. We can only change the orientation within planes locally when we make composite materials.
Mm-hmm.
But when you look at the complexity of natural materials, you can have 3D load cases, 3D reinforced orientation of the fiber. And I realized it's impossible to do this with composites. So you really need to re-establish new manufacturing technologies and new materials engineering approaches. And searching for this complexity and sustainability together, I just kept evolving and evolving to the point now where I am, where we are trying to use biotechnology and grow the reinforcements as we need them.
Yeah.
And I'm really excited about this because...
and was there a moment in time that you thought, okay, we should take a left here instead of continuing the fixed way of thinking of this composite design? For you personally?
For me personally, this was around 2016, where I completely took a right turn in my career and went to an academic environment which embraced this crazy visionary thinking. Yeah. And I took the chance to relearn.
And if you do the crazy visionary thinking, what is the reaction of people?
It really motivates me. When I speak to composite industry experts, I'm really excited because they tell me, you're doing exactly the thing that we have no clue how to do. Please keep going on that thing.
Okay.
Don't do the stuff we can do,
Yeah.
And that gives me energy.
Yeah, that's exactly where the experimental side of the research comes in. Yeah. Cool. And for you, Baris?
In my case, so I was a postdoc. I was in Switzerland between 2016 and 2021. And I'm a mechanical engineer by training, and I spent literally 5 years there in a materials lab. It was at that time that I decided that I would like to stay in academia, because until then I was doing kind of what seemed fun. But when I was there, I realized manufacturing processes are interesting, but the materials come before that.
Yeah.
And with the training I got there, I think it opened a new perspective for me, and now I look at things in a more holistic fashion. And I realized that if I keep doing what I'm doing in a setting where I can bring materials and manufacturing research together, then I can have a broad impact. And I cannot speak of a specific moment, but training as a materials research setting was what made the change on my side.
Yeah. Okay. Cool. I think the other episodes I finish with 3 questions. I want to ask these 3 questions as well. I did not give these questions in advance, so it's just you can choose.
So we cannot cheat.
No. The first question is both teaching or doing research.
Both, but research more.
Okay. Yeah. And for you, Kunal?
I enjoy research more.
Yeah.
Yep.
Yeah. Thanks. Second question is: do you think the technology is already there, or no? We need more time to investigate what we are researching at the moment. In your field.
Yeah, we have the knowledge about the building blocks. I think we are all confident about our own building blocks, but we need time to bring things together.
Okay. Yeah. Nice.
Yeah, I would say in my case that the technology is not yet there.
Yep.
So the material systems we're working on are not yet mature.
Yeah.
But this makes it fun.
Yep. Last question. Not fly at all anymore, or fly consciously?
Fly consciously.
Yeah.
Yeah. Definitely fly consciously.
Yeah. And why?
I mean, in Europe, we have one of the best train infrastructure, for instance, across the world, right? So most of the time it works well, but when you go from country A to B and then to C, then things get complicated.
Yeah, because the reason I'm questioning is because I think every guest I'm speaking in my podcast is working in the aerospace department to make a more sustainable flight. That's funny.
So that we can fly more.
Maybe, but of course it's always the pink elephant in the room, right?
Yeah.
But nobody says, no, I work in aviation to make more money. Now, everybody here works in aviation to make it more sustainable, and that's what I like about it.
Yeah.
You want to add something, Kunal?
No, in an ideal world, everywhere over land we would take the train.
Yeah.
And I don't know, 5-6 years ago I had a strong feeling about this. I was like, why do we not just invest in more train infrastructure?
Yeah.
But now with the geopolitics, how it goes,
Yeah.
I realize it becomes really hard to protect your train networks and secure the infrastructure.
Yeah. Thanks both for being guests in my podcast.
Thank you for having us.
Maybe the most advanced engineering has been around a lot longer than we think. Not designed in the lab, but shaped by nature over time. And perhaps the real challenge is learning how to see it and translate it into something we can build. Thanks again for listening to Coffee with Martin, and tune in for the next episode.